Thanks. Welcome back. Today I want to start with a bit of foreshadowing. So we were talking last time about how to prove the topological four-dimensional Poincare conjecture. And I gave you two strategies, and we were focusing on the first one where we thought about how to prove a topological H-cobordism theorem. So start with a purely topological H-cobordism. How can we apply the Friedman strategy to it? There was a first step to it, which I kind of glossed over, but today I want to start by telling you how that works. So prelude, suppose you have a topological four-manifold and its homotopy equivalent to S4, then M and S4 are topologically H-cobordant. And so this would be then the analog of Wall's theorem, but purely in the topological category, and then we can apply our fully topological H-cobordism theorem to this guy. So in order to prove this, I have to give you a preliminary definition. So here it is. So let X be a topological space, not necessarily a manifold. I know that's a bit weird. And then we have some subspace A of X. We say that this is one locally co-connected, which is a mouthful. It's abbreviated 1 LCC. If the following, so whenever I have a point of A and a neighborhood U of A, then I can find for myself a neighborhood V contained in U such that I look at the inclusion map. So V is a subset of U. So V minus A is a subset of U minus A. So these subsets, this is contained in that guy. So there's an inclusion induced map on the level of fundamental group. And I want this thing to be trivial. And I want this to be trivial for any choice of base point. So what this is saying is that whenever I have a loop in this smaller neighborhood, it's trivial. It's trivial in this slightly larger neighborhood. So personally, I think this should be called locally one co-connected because it's a local condition. So we're looking really close to every point. It's co something because we're looking at the complement, and it's one connected because we're saying something about loops being null homotopic. So that's one way to think about this. And then a nice example of this is suppose you take any point inside of an N manifold where N is bigger than or equal to 3. Because M is a manifold, it has arbitrarily small neighborhoods that look like, in this case, our N is bigger than or equal to 3. So the complement of that point is like R3 minus a point, which is simply connected. All right, so this is something that sort of locally up to some notion of homotopy group is like a manifold point. Okay. So that's a bit weird. You might be wondering, why am I doing this? Let's go back and prove our theorem, the statement that I want to prove up top. So let's take M. Now I'm going to take the cone of M. Let's call this point V. So this is weird. We don't usually cone things in manifold land. And in particular, we're not quite sure what's happening at that cone point, right? That's a bit weird. But what we can say is that this thing cone of M is something called an A&R homology five manifold. I'm not going to write down a definition of this. Morally speaking, I suspect almost none of you have heard this phrase before, which is totally reasonable. Slightly, it's a topology thing, but it's a bit adjacent to what maybe this audience is about. Morally, you should think about this as an approximation of a manifold. Okay, so ANR stands for absolute neighborhood retract. So let me convince you that manifolds are ANR homology manifolds. So manifolds have embeddings into Euclidean space such that they have neighborhoods which retract onto that image. That's called the Euclidean neighborhood retract, ENR. And ANR is a sort of generalization of this, but manifolds are ANRs. And then homology 5 manifold, that means that at every point, I have a local homology. And the local homology of a manifold I know is either Z or 0, depending on the dimension. That's something I know about manifolds. These spaces have those properties. And an interesting question in a field of topology slightly adjacent to ours is to what extent are things of this form actually manifolds? Okay, that's just a lovely field of topology that, maybe I don't hear about so often, but it exists. So I have this cone. You can prove, which I won't, that it is this approximation of a manifold, 5 manifold. And the only non-manifold points is V. Because away from that V, this is just a product of M with the interval. So that's just a manifold. It's just that at this point V, we don't know what's happening. But I do know that V is 1 LCC. So how do I know that? Well, the definition says, given my single point in that set, you're supposed to give, here's some neighborhood U, but I can always find for myself a neighborhood V, which is like a shorter version of the cone. And then what I know is that V minus little v is homotopy equivalent to M, and M is simply connected, so it's 1 LCC. And then there's this super cool result of Bryant Lacker from 78, which says that this means that cone of M is actually a manifold. If all the potential non-manifoldness has a certain low dimension, which happens to be 1 LCC, these guys showed a long time ago that you honestly have an honest manifold. And now we're done, because now that I know that V is a manifold point, I can remove a little, maybe I should say topological, just to make that clear. I can remove a neighborhood of V, which is homeomorphic to R5, and the complement of that will be an H-cobordism from M to S4. So that completes our proof. Okay. So something that I find really awesome here is that we had something that has sort of certain properties of a manifold. And here we have a point that up to this sort of very weak homotopy condition has the property of a point in a manifold. And it turns out that, goodness, you honestly have a manifold. Okay. So now these two boards plus the topological H-cobordism theorem will complete your proof of the fully topological Poincare conjecture. Okay, so I will return to this sort of notion again. Questions about this before we return to our previous theme. I should have said Mark and Patrick are in the live audience again. Ben Rupik is in the live but not present audience. So feel free to ask questions in the chat. I'll ask them. If anything needs to be addressed, they're welcome to read it out or just unmute yourself.
So can you say again, where do you use that M is now homotopy equivalent to S4 at which stage?
So we only used it here. So here we use the fact that pi1 of M is trivial. So in that definition of 1 LCC, that thing, that domain guy, pi1 of v minus a, that thing is a trivial group. So that map is a trivial map. And the dimension of M was important. Like this result doesn't hold in all dimensions.
So, but does this then work for any manifold with pi1 trivial, or?
I mean, we also needed the fact that it's a homology 5 manifold. Like it's an ANR homology 5 manifold. So
okay.
there's more things happening in here.
Okay.
I certainly didn't prove this part. But it's worth noting that if you take a homology, good question. If you take a homology S4 here rather than a homotopy S4, then this thing will not be a manifold. And that's a good example of something that's a homology manifold, but not a manifold manifold. Fun fact, oh no, ask me later. But this sort of coning thing is a much beloved approach in this field. Other questions? All right, so let me return to what we were doing before. So we had been in the middle of talking about handle straightening. So this, or smoothing, sorry. So this is what I had talked about last time. So we had this notion of a handle smoothing problem, which is this topological embedding of an open K handle inside of a smooth N manifold, such that we knew that this map is already smooth in a neighborhood of the attaching region. By the way, I forgot to write neighborhood last time, but I said it, but in case that was confusing, that's what's happening there. In general, if things are confusing, please refer to the typed lecture notes, which correct some of these errors that I make when I speak. And we said that a smoothing problem can be solved on this core handle bk cross bn minus k. If there's a topological isotopy, the topological isotopy is going to start from H, the H that you have, the problem that you're trying to solve. So the starting point of the isotopy is that input function. The output is some H1, which I know is smooth on the core thing. And we know that this isotopy, we want it to be fixed on a neighborhood of the attaching region and outside of a compact neighborhood of the core. That thing is a big mouthful, so I'm going to abbreviate this to relative, the attaching region, relative boundary K cross Rn, boundary Bk cross Rn, and infinity. And the thing I tried to convince you all of last time is that if you could solve all handle smoothing problems, then you would get smooth structures on all manifolds. And then what we know is that these can always be solved that's that idea. So for n less than or equal to 2, 3, these are always solved. And then for n bigger than or equal to 5, these are solved if concordant to a solved problem. Now, I want to make a comment here. Here I'm talking about handle smoothing, which is about, I have a smooth manifold and a topological map. Can I perturb it to make it smooth? There's an analogous question that you can ask in the piecewise linear category, which asks if you have a piecewise linear manifold and a topological embedding, can I smooth it? So I said something a bit wrong here last time. That's why I'm making this point. For k not equal to 3, these PL problems can always be solved. Okay, so last time I said that was true for the smooth thing, and that's not true. So let me correct myself there. By the way, that business about k not equal to 3, that's precisely related to the invariant called the Kirby-Siebenmann invariant. There's a long, beautiful story there, but let's not get into that. those are called handle straightening problems, in case you would like to look those up. Okay. So this is where we were at. Now I want to tell you what we can do in the dimension 4 setting. So it turns out that even if you can't solve all the handle smoothing problems, you can still get a lot. So for example, this fact that in n bigger than or equal to 5, you can solve some of these problems, that's what leads to a lot of this beautiful Kirby-Siebenman theory. And for example, yesterday, it was mentioned a couple of times that high dimensional manifolds, compact high dimensional manifolds have only finitely many smooth structures. That, for example, comes from this by a long, beautiful route. But that's at the heart of that proof. So it's going to be similar in dimension 4. We won't be able to solve all the problems, but we'll get far enough that we'll still get something quite neat. So here's what we'll get. This is a theorem of Quinn. And this says, suppose you have V4 smooth, and you have a problem each dk again, as usual, it's already smooth on a neighborhood boundary bk cross R4 minus k. That's just the thing that makes it a handle smoothing problem. For low values of k, things are quite nice. So for k equal to 0 and 1, we know that h can be solved on vk cross n minus k. So what that says up top, that definition, for 0 handles and 1 handles, things are very nice. Okay. For 2 handles, things are a bit weirder. You can solve H in a sense. So H can be solved, but not on this, but on something on W, where I'm kind of defining this, okay? So where W is either, sorry, so W is a neighborhood of BK cross 0 after either one of 2 possibilities. You either have a topological ambient isotopy, relative to boundary BK cross Rn minus K and infinity, or a smooth regular homotopy. So let me sort of specify what I mean by this. So this means that there exists an isotopy, topological ambient, topological isotopy, HT, such that H0 is equal to H, HT is relative, okay, let me just write that there, relative boundary BK cross R4 minus K and infinity. So the isotopy is what has this relative property that we've always wanted, and it starts from H and goes to some H1. But now all I know is that H1 is smooth on W. So this is we can't solve the two handle smoothing problem, but we can do this. Okay. Questions about this statement? It's a mouthful. We're going to talk about applications in a second. But so I have this, okay, so hopefully 0 and 1 is reasonable. It's like you can just solve those problems, that's fine. And then for two handles, you can't solve it on the actual core of the original handle, but you first move that core. You either move it by a regular homotopy, meaning smooth finger moves and Whitney moves, but whatever, there's some smooth move that you can do to that core, no longer embedded, but it's some smooth thing, and then that gets smoothly embedded. Alternatively, you can move that core by a topological ambient isotopy to something weirder looking, different looking, and then that thing has a neighborhood which gets smoothly embedded. So it's, you can't smooth them, but you're doing something close to it. Okay. So I want to convince you that this is still very powerful. So let me convince you of it by stating some corollaries. The first corollary is the four-dimensional annulus theorem. It says that if you have a collared embedding, so let F be a map from D4 or B4 to the interior of D4, which is a collared embedding, that's a topological embedding, then D4 minus F of int D4 is homeomorphic to that dimensional annulus, which is S3 cross the closed interval. So maybe a picture here might be helpful. This guy, that's the codomain, that's a D4. And then F is mapping in this littler D4. And that's something like this. And so you might think of this as like there's the Schoenflies question, and then the annulus question is the next one over. Collared embedding, by the way, means that there's this, I can actually extend this over to a neighborhood like this. And the outcome is that this complementary region between these two dudes, that's actually an annulus. So this is a really big deal. In high dimensions in the topological category, this was a result of Rob Kirby. This is, again, where he used the torus trick for the first time. And then maybe to convince you of why this is interesting, a corollary of this is that connected sum of oriented topological core manifolds is well defined. Both of these are exercises, by the way. And it's not so hard to prove using that first part of Handel's Riemann.
Aru,
Yeah.
before you erase something,
Yeah.
can you just say, you said something really nice out loud that I don't think you wrote down about one locally co-connected. Can you say it one more time?
Do you know what it was?
I think you just gave some intuition for what it was.
So I like to think about it as locally one co-connected, or perhaps locally co-one connected. I don't know if that was the nice thing. I think it's nice. I think it's local because this is local because you're looking at these small neighborhoods. You want these loops to be null homotopic close to A. Like those loops don't get to be null homotopic far away inside of my space. It all has to happen really close by. So like remembering covering spaces or something, you might remember, locally path connected or semi-locally simply connected, those things. That local always meant you're looking really close to A. So these U's and V's are making things really close to A. So that's why it says local. It's co because we're looking at the complement of A. We're talking about like how that complement looks. And then one connected because it's about, loops being null homotopic. So it's something like simple connectedness of the complement. Of course, this can be changed to K locally co-connected, and you replace just this guy by this one becomes a K instead. Did that help? I think a nice way to think about this is you should think about locally flat submanifold, subsets. So if you have a locally flat submanifold, it will have this sort of property. And that's a nice exercise, actually. Did that help?
It did, thank you.
You're welcome. I'm going to erase things if that's okay. Okay, so there is a question in the chat apparently about to what extent do we know connected sum of 3 manifolds? Smooth manifolds. Smooth manifolds and non-orientable manifolds is well defined. Those are great questions. So for smooth manifolds, the annulus theorem is not so difficult to prove. So you could consider doing the same exercise in that category. Alternatively, there is a result of Tali called the Tali disk theorem that tells you when you have smooth embeddings of disks in a smooth manifold of the same dimension and with the same orientation behavior, then they're isotopic smoothly. So that's how you can show that connected sum of smooth manifolds is well defined by using the Tali theorem. And then the orientation condition is a nice thing to think about. The reason, like you can run the same argument, connected sum of unoriented manifolds. Am I saying that right? Non-orientable manifolds really is also well defined. But the thing to think about there is like CP2 connected sum CP2 bar is not homeomorphic to CP2 connected sum CP2. So there is something weird happening there with orientations. And so there's something to be careful about there. But these are excellent questions that you should consider asking one of your TAs. Okay, other questions? Reconnected sum. There's a recent sort of survey paper of Chuck Livingston that talks about connected sum, which I think is a very nice resource. Another great resource, not just for this, but for virtually anything that I'll talk about in lectures 3 and 4, is a very long survey paper, very long and detailed and beautiful survey paper of Stefan Friedel, Matthias Nagel, Patrick Orson, and Mark Powell. It's called Survey of Foundations of Topological for Manifolds or something like this. Check their websites, you'll find them. Okay. All right, so let me do the next thing I want to do, which is to prove this theorem of Quinn. This is another corollary of Quinn's handle smoothing. This is the one I promised you last time. Suppose you have a manifold which is connected and non-compact. It's smoothable. And let me give you the thing that I'm going to prove is the following. Following claim, there exists a discrete set S containing points S alpha inside of M, such that the complement of S is smooth. So there are some number of points inside of my non-compact manifold, and away from those points could be infinite, just want it to be discrete, such that the complement is smooth. And so first, here's the proof modulo the claim. So there exist locally finite disjoint proper flat rays, no relation, R alpha from 0 infinity to m with R alpha of 0 equal to S alpha. So that means if this is my non-compact manifold M, here are my points, S1, S2, S alpha. Locally finite disjoint flat, that's fine. Proper means they go off to infinity. Okay, like they don't get to like loop around. They actually have to shoot off to infinity. And then the point is that if I take, what do I want to say? So if I take the complement of these rays, so here's all of these rays, that's R1, R2, R alpha. So I take all of these, I take the complement of that. So first claim is that this is a subset of M minus S. That's not surprising since that's S. And this is smooth. So this is smooth. And this is open. That's a subset open submanifold of a smooth manifold. Therefore, this is smooth, but this is homeomorphic to M. This requires thought and proof. I'm certainly not providing any proof, but you might think about R2 and removing the positive x-axis out of R2, and then this, right? So remove the positive x-axis from R2. This complement is still R2. You can kind of build yourself a homeomorphism by, like you're kind of retracting the positive x-axis off to infinity. Like instead of removing the positive x-axis, remove the arc from t to infinity, where t goes to infinity. Okay. All right. So what I hope I've convinced you of here is that if I prove the claim, then I'll be done. So I get to smooth my manifold. The non-compactness really came in here, right? Like I was able to, anyway. So if I prove the claim, we'll be done. Okay. So here's the proof of the claim. This will be much like last time, except not quite. So proof of claim. So once again, consider charts. Now these are our 4 charts going into M. Now I really do want to specify that it's locally finite because it's necessarily not finite since it's not compact. But they're countable, if you wish, coordinate charts. And like before, we define uj to be the union of these guys, of these images. And again, just like before, I have u of j minus 1. What I need to convince you of is that by induction, we assume this thing has a smooth structure away from some points. And I need to, well, here's some points. So assume that there's an Sj minus 1, some discrete set. such that this complement is smooth. And I have this next guy coming over, that's Hg of R4. What I need to convince you of is that I can somehow extend this smooth structure over to the next thing. But I get to pay a price. I get to do this outside of a discrete set of points and still be happy at the end. Okay. Idea makes sense, more or less, right? I have a weaker tool than last time, but I'm also aiming for something weaker. So it's not so harebrained. So what I do to proceed is I pick, so choose V in R4, a codimension 1 smooth submanifold such that the image bicolored, such that Hj of V is going to separate these two portions. So let me draw it for you first. So V looks something like this. So that's V. So Hj of V separates this side from that side. So what are they? They're Uj minus 1 minus Hj of R4 and Aj of R4 minus Uj minus 1. So I want to apply Quinn's handle straightening to this. So apply Quinn's handle straightening to V cross a bicolor. And it's bicolored, so it has some color here. And by that I mean I'm looking at V. V is codimension 1 in R4, so this is a smooth 3 manifold. And I'm applying handle straightening to each of those handles, similar to what we did last time. Admittedly, didn't go into a lot of details. Check typed lecture notes for details. So I'm going to try to apply it to all of those handles, but I only get to apply it up till handle 2, handles of index 2, because those are the only handles that I can say anything about. So what I get after doing this is the following. I get an isotopy of Hj to some Hj prime, which is fixed outside Aj inverse of Uj minus 1. So away from this overlap, nothing's happening, but V was only in that overlap. So that's the only place anything ever happened, such that Aj prime is smooth on a neighborhood of the 2 skeleton of V prime where V prime is obtained from V after a topological isotope. That's what that first little dash is saying. This is saying, you know, do the normal thing on the 0 and 1 handles, but on the 2 handles, so I'm only going up to the 2 handles. On the 2 handles, I don't get to straighten, but I do get to change my V to something else by a topological ambient isotopy. And then on the neighborhood of that 2 skeleton, the result is smooth. Okay. All right, that's a lot. Okay, so what this is saying is that I had this V was over here.
So sorry, Aru. So in that picture, that should be HJ of V, and somehow
Yes.
we're discussing now just in the chart.
Yes, thank you. Good point. So in R4, V will be something like that. Okay. And then what this is saying is that, thank you, Danitza. This is saying that if I get to move this somehow to some V prime, such that AJ prime of V prime, this has a neighborhood. This, you know, these are both bicolored. So I had to move my V to a V prime, and I had to change my function to an 8J prime. But 8J prime on a neighborhood of V prime 2 skeleton is actually smooth. Okay. Okay. How is everyone doing? How are the faces looking? Okay. All right, we're almost done. Now we're going to use this cool fact about 3 manifolds. The cool fact about 3 manifolds is that the complement of the 2 skeleton of a 3 manifold is a collection of balls. And so what I know now is that I have this 3 manifold, and away from some balls in there, I have something that's a nice and smooth embedding. And so what I then do is, you know, all of this can be, the smoothing can be done very close to the original stuff. So you make sure that this V prime is not so far away from V. And by doing that, because you know that this Sj minus 1 is discrete, you make sure that this thing still separates this, these 2 regions, but it also doesn't intersect Sj minus 1. And so to sort of boil this all down to the end, this says that we have smooth transition functions away from the centers of these BLs. Maybe transition function away from the centers of these BL. And so that means that Uj is smooth away from Sj, or Sj by definition is Sj minus 1 union these centers. Yeah. Ah, thank you. Thanks for that. That should say smoothing. Smoothing. Thanks. All right. So the big picture idea is, you know, cool fact about 3 manifolds is that if you can do something in the 2 skeleton, that means you're really only missing out on some points. And then points are allowed. That's the price you're willing to pay. Okay. That's the end of this. Questions about this?
I'm a bit lost why this argument is about 4 manifold V cross the interval and not just V. I mean, somehow we're jumping back and forth.
Yeah, so I need the fact that I'm thinking about a caller of a 3 manifold so that I can sort of tell you this fact that it's only balls that are missing. Like there are no 3 and 4 handles to worry about. So that was important here. And then I needed the caller because like V prime isn't necessarily a smooth thing anymore, but this neighborhood is. And when you're doing this patching over, you want to patch over by like an open neighborhood. Like there are many details that I'm skipping over here, but I do think the fact that you're doing it on a neighborhood is important so that you can actually like, do you know what I mean? Like when you're patching up
Right, yeah.
things, you want to be able to do it on open dudes. But the fact that you can get this 3 manifold is also important so that you can actually do it handle by handle. But you have to stop at 2, but that's enough.
Right, okay, thanks.
You're welcome. I'm very happy to talk about this more, by the way, but maybe not immediately. Okay. Other questions? Okay. Promise I'm not a conspiracy theorist, but I'm going to fill up this board a little bit, okay? And we'll see how this works. We talked about this. So handle smoothing implies the annulus theorem, and that from there you see that connected sum is well defined. And then hopefully I just convinced you that handle smoothing implies non-compact smoothing of non-compact 4 manifolds. There are at least 2 more fundamental tools that I owe you. And you might be wondering where those come from. And then you might be wondering, well, where does that come from, right? Like handle smoothing was really cool, but why is that true? So I want to tell you something about this. But first, I want to add another box, the third thing, which I missed writing. This is a pretty straightforward corollary that the immersion lemma will follow from this. Sorry, that was the first fundamental tool. This is saying that if you have a continuous map of a surface into a 4 manifold, then you can perturb it until it becomes in topological immersion. So these are all exercises. So let me say a little bit more about the next thing, but I need room, so let's do that first. So here's the statement. Okay, so immersion lemma, that's an exercise now. I want to talk about normal bundles. Oh, hello. So here's the statement about normal bundles. that I want to talk about. It will look a bit weird, so hang in there. So let X be a topological space again. And you have some closed subset of X. I'm going to ask for a few things. I'm going to ask for X to be an A and R homology manifold, for manifold X, that's right. X minus A to be a manifold. A cross R to be a manifold. And then finally, there are two possibilities for 4. If the dimension of A is not equal to 2, then I want A to be 1 LCC. And if the dimension of A is actually 2, then I want something that's kind of similar. But let me write that down. Then I would like for all A in A and for all neighborhoods U of A, there exists neighborhood V in U, such that the image of pi1 of V minus A going into U minus A is infinite cyclic. That all seems very random, but then the payoff of this is that then A has a normal bundle in X. There are many questions you probably have about this. Let me try to avoid many of them. By a normal bundle, I mean that there's a neighborhood which is like the total space of a vector bundle over A. You really should think about this as like the analog of normal bundles that you have in the Smith case. So I claim that basically this thing will tell you that locally flat submanifolds have normal bundles. That's the technical version. And you kind of apply this in a certain way to get this. The proof of this, I'm going to skip sadly. I was only going to sketch it anyway. The proof of this is going to need 2 components. And one component is this non-compact smoothing. The other component is the thing that goes over here. So let me try to give you a super sketchy version of this theorem. Like you have A inside of X, and you take the product of the whole thing with R. So you have now A cross R inside of X cross R. And what you do is you use a high dimensional theorem, high dimensional existence of normal bundles to see that there's some normal bundle for A cross R inside of X cross R. And then you look at a neighborhood of this thing. You remove the A cross R from this guy. It turns out to be a non-compact H-cobordism. And so the input that you need from this is a non-compact H-cobordism theorem, which will tell you that this thing in X has a normal bundle. So the thing that goes over here is a non-compact H-cobordism theorem, and it's called the controlled H-cobordism theorem. So these two together will prove the existence of normal bundles. And turns out that's precisely what you need to prove Handel smoothing as well. And then finally, for topological transversality, that's the last remaining ingredient. This will need this guy. It will need normal bundles. And it's going to need one more thing. This will need that skyscrapers are standard. That's what we used in the proof of the disk embedding theorem. We'll need that one too. So combining those ingredients, we're going to get that. You might be wondering, well, where does this come from? That comes from this. Okay. So this is the big insight of Friedman. Friedman showed that these infinite objects are actually disks, 2 handles. So this is awesome. You can prove a lot with this. But then Quinn came along and he proved this non-compact H-Topologism theorem. And once he proved this, you got connected sum well-defined, non-compact smoothing, fundamental tools. These go into the proof of the Poincare conjecture. That's very exciting. Alternatively, if you wish, you can also do a direct proof. You can go directly from there into the fully topological four-dimensional Poincare conjecture. All right, so we only really talked about this corner, but that's where all of the rest of this comes in. I want to end by doing something slightly different. I want to end by showing you why I was doing that foreshadowing at the beginning. So this normal bundle stuff maybe seems a bit random, but it turns out you've been using it secretly many times. So I want to tell you how you've been doing that. And so here's the theorem of Friedman that you've probably heard of, perhaps. It says that every integer homology 3-sphere call it sigma, is the boundary of a compact contractible topological four-manifold. So I want to tell you how this works. This is not Friedman's original proof, but a different one that I happen to like. And it's the following. So I'm going to start with sigma cross interval. And for convenience, at the moment, let sigma be the +1 surgery on the right-handed trefoil, if you like. That's the Poincare homology sphere. And I know that the fundamental group of sigma is normally generated by a single element, namely the meridian of the right-handed trefoil. And so I'm going to do something to this sigma cross I. This has 2 boundary components, which are sigma. And so that generator of fundamental group, that's represented by some curve, which I'm going to push into this interior. And then I'm going to do surgery. So that means I'm going to remove an S1 cross D3 neighborhood and glue in a D2 cross S2. So in that result, I still have sigma on the 2 boundary points on the boundary components, but now this alpha bounds a disk, namely that disk. And then there's that S2, it's right there. Of course, it's a homology sphere, so this thing was the boundary of a surface. Now this thing is simply connected. And if you think about it a bit, it turns out that its H2 is Z plus Z. Well, because it's simply connected, these guys are represented by spheres. And one way to see that is that, like a basis of homology for this surface, these guys bound disks, because manifold is simply connected. So you can contract that surface down to get spheres instead. So now I have a situation like this, where once it's still sigma sigma, but I have my homology is generated by something like that. Then we talked about the disk embedding theorem, but it turns out there's something called the sphere embedding theorem. And the sphere embedding theorem tells you that this thing can be replaced by an embedded sphere, and then this partner is still around. That partner intersects it precisely once. That's important. We haven't talked about that before. And then now I do surgery on this thing, which means I remove an S2 cross D2 and I glue in a D3 cross S1. I'm doing surgery on this circle. Really hope blue is visible, is it? Okay, thank you. So now I do surgery on this sphere, and the result is something I call W, and W is simply connected, and its H2 is 0. Now, H2 is 0 because I sort of intentionally killed all of the H2. Pi1 is 0. That's interesting. That's because of this friend over here, by the way. So worth noting that we use that. All right, I'm a minute over, but I'm going to write the punchline. So let me just do that and finish. Now I have that W. That W is like a very nice puzzle piece. I'm going to take an infinite number of copies of W and 1 point compactify. So notice I always had sigmas on the boundary components, so I can glue them together. When I do this construction, this infinite construction, I still have that sigma on one side. Morally speaking, this wants to be the cone on sigma, okay? But we talked at the very beginning that the cone on a homology sphere is not nice because it's going to miss out on some property, and that's why we had to fix it up by doing something on these puzzle pieces. And what we did is we killed all of the interesting topology in there. And so this thing, this fails to be a manifold, or this can only fail to be a manifold at that point infinity, but infinity is 1 LCC. For the same reason that it was last time, the dimension is not equal to 2, so I'm satisfying this. Infinity is a point, so point cross R is a manifold. The complement of infinity is a product of a manifold with many of those manifolds together, it's fine. And you have to check that last thing, but you do. And so that's it. That's all right. Thanks for your patience. This is basically all the mathematics, really, the proofs that are in this course. Tomorrow will be much more of a survey. We're going to talk about some results, not really going into statements of anything. So today was the sort of densely packed with mathematics day. Tomorrow, if I've lost you, please come back tomorrow. Thanks.
Let's thank Aru. Are there any questions for the speaker?
If you start with S4, a topological S4, and you start with a topological, homotopy S4, and you do the smoothing, say by removing 1 point. Is there a restriction on the smooth structures on the resulting R4 by the smoothing operation?
So are you saying, well, when I remove the point from S4, I get R4, right? Topologically, it's an R4. So I know that I'm looking homeomorphically at R4, right? So are you saying from the procedure?
Yes, but you're doing a particular procedure to produce a smooth structure.
Oh, that's interesting.
I mean, it seems to me well, I don't know anything, but if you're going to produce like a H-cobordism between that and something standard, I mean, that was what you said about Friedman's original proof. Doesn't that imply that there's some type of restriction on possible smooth structures?
Think so. I would say that so I assert that, do I assert this? So I'm asserting that if you have any, so let R4 be an exotic R, okay, let R be an exotic R4. And I claim that Friedman showed that beautiful R and R4 standard are smoothly properly H cobordant. But all I know about this thing, this is simply connected and simply connected at infinity. But all I know about that H cobordism by Friedman's theorem is that it's topologically a product. So that's only going to tell me that beautiful R and R4 standard are homeomorphic. So it's not.
That's really
clear to me
great.
that
That's, you know, anyway, that's really great. Thank you very much.
You're welcome. But I think this is an interesting question of what sorts of smoothings you can get out of here, and I would expect that there's really no control. That's my guess at the moment. I mean, it is still, and I think this was mentioned maybe by Paul, by someone, that it's still possible that it's a conjecture that every non-compact four manifold admits uncountably many smooth structures. So it's that's plausible. And I think it is known and almost certainly a result of Bob Gompf that if you take a closed four manifold and you remove a point, manifolds of that type always admit uncountably many four manifolds. So I think, but I personally, I think smoothings of non-compact four manifolds are interesting and more people should study them, not just for R4, but general four manifolds. Other questions? Lost everyone. Flowchart. Cool.
Okay, let's thank Aru again. And so at this point, we'll take a break heading into lunch, which today we'll have rooms set up to discuss the research talks, but we'll return after a 10-minute break, I think. So at 12:40, those breakout rooms will start.